Well, hello, Griffins. Video 4, Kinetics unit. After video 4 today, you will be able to read and interpret potential energy diagrams. This is an important skill and a piece where the memorization is going to come in handy right off the bat. So, potential energy diagrams show reaction progress on a timeline. And here's an example. So, the reactants are here, because that's where the reaction starts. I have to add energy now, and I can track now how much energy I have to add to get from 50 up to 100. Okay? And then this is the activated complex, and then the reaction goes, and down here is the product. So that's always going to be the case. I'm going to have reactants on the left, I'm going to have products on the right. The difference is actually the most important part. This piece here, whether the arrow's in the middle, whether the arrow's on the left, or whether the arrow's on the right, all means the same thing. That is the difference between the products and the reactants in terms of potential energy. Okay? And that last one that we saw was endothermic because it started up, or exothermic, and heat left. This one is endothermic, sorry, because I saw it and I couldn't keep that word out of my mind. So here the reactants start on the left. We add heat and the products end at a higher heat. So energy must have went into the system. Okay, so endothermic, it absorbed energy. And when I do products minus reactants, I'm going to see 50 minus 20 is a positive 30. Positive delta H, endothermic. That doesn't change from our previous learning. Okay, some other important things to know. Forward reaction now reads from left to right, reactants to products. If I reverse the reaction, which happens with these equilibriums, I go backwards now. I got to go from right to left. And you notice, and sometimes I have a bigger hill to climb. Okay. Activated complex is a noun. This is just the top piece, the highest point on the roller coaster, if you will. It's a specific point, and that's it. Activation energy is how much energy it takes to get from the reactants to that activated complex, to that peak. And it's going to change whether I'm going in the forward reaction or the reverse reaction, as you just saw in those two pictures. Okay? That was okay. All right, catalysts are special class of compounds. By definition, they provide a way to lower the height of the peak, making the reaction happen faster. What we say is the actual scientific term is they provide an alternate pathway. Okay, because what happens is the chemicals, potential energy changes, and at that activated complex, they're actually neither or. They're no longer reactants, they're no longer products. And then they go, and once you start to fall down the hill, the reactions happening and the products start forming. Okay, the catalyst will provide an alternate path that makes them rearrange differently in a way that uses less energy. Okay, that's the actual scientific definition of what's going on with a catalyst. Overall heat of the chemical reaction, we need to do this specifically. It's always products minus reactants, and that's wrong. Okay, this is wrong. You need to cross that out. It's definitely products minus reactants. You need to do it that way specifically so that the sign happens correctly. And I'm sorry, that's an artifact left over from last year that was wrong. So products minus reactants. You need to make sure that's clear. You can't get that wrong. And that is not in your reference tables. So let's make sure we get that right. This is from our previous learning, right? Positive delta H is endothermic. Negative delta H is exothermic. That is something we already kind of know. Okay. I'm not sure if that showed up over my Facebook. Maybe that's good. All right, labeling important parts of the potential energy diagram. So this is a piece you need to be able to do. Take very careful notes. Potential energy is always on the y-axis. Went too fast. And you're going to, here's a particular potential energy diagram. Starts low, finishes high. Okay. I know that the potential energy of the reactants is 10. Okay, can you see that it's 10? Okay, good. And the potential energy of the products is about 35. If you want to say 36, that's not going to break my heart. Okay, good. And now this difference in it, like I said, it doesn't matter where I put it. And that's why I did that graphic like that. That is the delta H. That's the heat of the reaction. Products minus reactants to get a number. Okay. Top piece, activated complex. You need to put that in. Activated complex. Okay. The activated complex does have a particular energy associated to it. So this energy going from reactants all the way up to the activated complex is called the activation energy, specifically in the forward reaction because I'm going left to right. It will be the normal activation energy. This would be the activation energy specifically, though, in the reverse reaction. Okay, so if I went from products and went back to reactants, I would need less energy to make that happen, as you can see. Okay, good. Exothermic potential energy diagram. The labels are going to be the same. What is going to change is just that the reactants are going to start with more energy and I'm going to end with less. Energy is given off during exotherm. Exo is exiting. So the reactants are still on the left. The products are still on the right. But this time when I do 20 minus 33, I get a negative number showing me that it's exothermic. And I hope you all are listening to that because it's not written there and you need to, that's one of the hugest pieces. Delta H is why we actually do these potential energy diagrams. Okay. And so here's the delta H, doesn't matter left, right, or middle where I draw it. When it's between those two dotted lines that extend all the way across the page, that is my heat of reaction. I need you to not get confused about where I label these things. They can be labeled left, right, center, but they mean the same thing going from one line to another. That part doesn't change. Activated complex is what's on top, of course. Okay, got that. This is the activation energy in the forward reaction. Notice I don't need as much energy to make an exothermic reaction go. I just need a little bit, get up to the top of the hill, and off it goes. I like to use the analogy of how much energy does it take to get the shopping cart to the top of that hill? And once I get to the top of that hill, do I have to put in energy or can I just let go and watch the shopping cart go? Right? And that's kind of how these things work. This is the activation energy now in the reverse reaction. Notice the dotted lines are there. We're going to do a lot of dotted lining. That's it. So these are all the important parts. What I need you to focus in on is, by definition, which is the delta H, which is the activation energy in the forward reaction, what is the potential energy of the reactants. And I can label those up in any way. So if I give you this chart with the arrows, I can shuffle the arrows all around, but they're going from a specific line to a specific line. And whenever that happens, that's your cue to what it actually is. So that's what we need to get learning on. All right. Peace out. Press